Hello everyone. So this is the poster presentation registration number 304. So 90 to 95% of the hydrogen is currently produced from fossil sources. So this is the solution that I've provided by modeling alkaline and solid oxide electrolyzers using MATLAB integration and Aspen custom modeler integration. So this is the model of alkaline electrolyzers that you are seeing on your screens right now. So this block B1 is the stack of the alkaline electrolyzer which has been built in Aspen custom modeler. So I'll show you the Aspen custom modeler code. The input and the output ports have been defined, various equations have been defined for V cell, mass balance, energy balance and outlet ports. So this is my Aspen custom modeler block stack of the alkaline electrolyzer. So I've built the BOP of the alkaline electrolyzer as well. So after the stack, on the cathode side most of the hydrogen goes, and it contains impurity of water and KOH. So I provided a flash separator allowing some pressure drop, and the water and the KOH, the alkaline water, is circulated back to the stack so that the cycle keeps on going. And here I have provided a makeup water, and using the calculator the value of makeup water comes out to be 87.7 kg per hour, and this is a 500 kilowatt alkaline electrolyzer. So after the flash separation we get a stream which contains very much less amount of water than the previous one, but now there is some oxygen impurity that is present in there. So this stack has been built for 25 bar pressure and 75 degrees Celsius, the alkaline one. So for the oxygen impurity we have provided a kinetic reactor which reacts with the excess hydrogen, and this oxygen is well below the lower explosion limit, as we can see in the results. If we look at the mole fraction, so there is some oxygen present which is around 1.2% and which is safe, well below the lower explosion limit, but we need to remove this impurity. So through kinetic reactor we react this oxygen with the excess hydrogen and water is produced. And if we look at the H2 outstream now, it will be devoid of oxygen. As you can see in the mole fractions, oxygen impurity has been removed. Now only hydrogen, which is around 95%, and water is present. So after that we have provided a water separator, a simple separator to separate the water, and two streams pop out from here. One is the stream of water that we have removed, and next is the pure hydrogen. So if we look at the mole fractions now, so it is around 99.99%, which is the industry standard for the purity of hydrogen. So the magic number of 4 nines have been achieved, and this is my alkaline electrolyzer. Now coming back to the solid oxide electrolyzer, I've built the stack rather than in Aspen custom modeler, now integrated it in MATLAB. So as you can see, all the equations have been provided for overpotentials and cell voltage and power, and this calls on the Aspen files. When we run it, the Aspen file automatically opens. So the integration is better in MATLAB if we are looking to change the parameters, but since the Aspen custom modeler builds the native blocks of the stacks here, so the industrial integration of components is much easier in ACM or the Aspen custom modeler. But if we want to play with parameters, then MATLAB is preferred as a user. So now coming back to the solid oxide electrolyzer, the coding has been done. This is the stack part, and here goes the cathode where majority of hydrogen is produced. This side is the anode. Now the BOP is a little different than the alkaline electrolyzer one, because here the temperatures are 848 degrees Celsius and 1 bar pressure, which is different from alkaline one. The temperature was 75. So now we need to cool back the water, or the steam rather in this case, so that we can separate it from hydrogen and get a pure hydrogen. So we have provided a heater, but if the pressure was around 5 bars, the pressure is very less in this model, so we could have also provided a turbine which could have condensed the water back and provided a hydrogen stream. So now looking at the stream S2, it contains now water and hydrogen and some oxygen, so 85 degrees Celsius and 28 bar pressures. So we have provided a flash separator with some pressure drop of around 0.5 bars. As you can see, 27.5 0.5 bars of pressure drop has been provided. So this stream is the water that has been separated. Now this stream contains some amount of water and oxygen. Let's have a look at the mole fractions. So the hydrogen is 97% pure here, and oxygen is around 0.4%. So we are safe with the lower explosion limit now, and we need to separate this oxygen. So similar to the case of alkaline one, we have provided a kinetic reactor to react the oxygen, impurity of oxygen, with the excess hydrogen, so that in the next stream we only get water and hydrogen. So hydrogen purity is dropped, but because of the increase in water, but oxygen impurity has been removed. So after that, to get it to the industrial levels of magic of 4 nines, we have provided a separator so that pure hydrogen is achieved here and the water is removed. So if we look at the stream S6, the results, now the mole fraction, the hydrogen comes to the magic number of 4 nines, 99.99% at least pure. So this is the modeling that I've done for the Aspen Academic Innovators Challenge. Thank you.